I think everyone's back, so we can probably just go ahead and get started, except Tom, but. So we're really happy to have Dag Normann from the University of Oslo, who's going to talk to us about quantifiers and real analysis. So take it away, Dag. And we have the mic on. Can you hear me? Dag?
Yeah, I can hear you.
Okay. So go ahead, you can take it away whenever you're ready. You can go ahead.
I'm ready. You want me to start?
Yeah, yes, you can go ahead, yes.
Okay, thank you very much, and thank you for the invitation to attend this workshop. I'm very sorry that I cannot be there in person, but still to Martin and his 60 years. And in a period, I had some very good and productive discussions with him, for which I'm very grateful, and I will come back to a few of them now. This is not really going to be a technical talk. It's going to be indicating some directions in the foundations of mathematics, and based on my research jointly with Sam Sanders over the last about 10 years. So let's go back to Cantorian set theory. In my view, they offered two tools for mathematical constructions. One is the introduction of ordinals that made transfinite recursion mathematically sound. And the other is that with a proper set theory, the power set and so forth, you can have definitions involving higher order quantifiers and higher order parameters. And that's possible, and they could study new classes of objects and describe operations with them as inputs. And a typical example are the two proofs of the Cantor-Bendixson theorem for closed sets of reals. You can, by transfinite recursion, remove neighborhoods containing one and one element of the closed set, or you could alternatively say that you remove all neighborhoods containing countably many points of the set. And one is a large transfinite recursion going maybe all the way up to omega 1 third Kleene, if the compact set is nice. The other is a one direct construction, but the use of quantifiers is much more heavy on the second and approach most popular by students. So that's one example of the two distinctions of the two sort of tools. So let's look at the Kleene quantifiers. E2, that's quantification over the natural numbers, and E3 is quantification over the continuum. And in computability theory, higher order search, we are normally studying those two quantifiers and even higher order quantifiers. And they are clearly non-computable. And, well, one reason could be that the scopes are infinite. But Martin Escado proved that for every closed ordinal alpha less than epsilon 0, there is a closed subset X alpha of 2n, or order type alpha, such that the quantifier over the set for every existential quantifier for every subset Y over on X is compute definable in Gödel's T. This has been mentioned in a prior talk here as well. And we say that this X set X alpha is searchable. So you have definitely infinite sets for which quantification over all predicates are computable. There is also then a selective function nu alpha definable in T such that u alpha y is defined for all y, and it selects an element in y if there is X alpha intersected with Y is non-empty. A set X has to be closed and countable in order to be searchable or to admit its computable selector, even with respect to if it looked at PCF definability or Kleene computability. And actually, Kleene computability is the thing that would work if you're considering all predicates, not only continuous ones. Well, Martin conjectured, and I proved that when X is searchable in T, then the Cantor-Bendixson rank of X is bounded below epsilon 0. And I also proved, which is a much more simple proof, that for any closed computable ordinal alpha less than omega 1 Church-Kleene, there will be a set X alpha or order type alpha such that this set EX is Kleene computable. So, but that is about the limit of it. A new theorem, you could call it new. If we tie up some loose ends using techniques that we have established, we have the following theorem. If X is a subset of 2 to the n, the following are equivalent. X is closed and countable, and the functional EX is computable in some f in n to the n. And I said exercise is just for those who like to tidy up this mess, because it's quite elementary proof based on the results you probably all know. But what you should note is that this quantifier is a functional of type 3. So we're talking about genuine objects of type 3 here. So in a sense, we need the concept of higher order computability in order to make sense to this theorem. The conclusion is that it is possible to have effective quantification over some infinite set, but if we want to understand complexity of quantification over sets that are not both countable and closed, we need some other tools. And I suggest tools from generalized computability theory or even something even more fancy. The aim of this talk is to describe some of these tools without going into technical details. And I want to explain why we or I are interested in them. Okay, in my project with Sam Sanders, we asked two foundational questions. The one is in the tradition of reverse mathematics. Given the theorem A of ordinary real analysis, what is the minimal set of axioms now in Kollenbach's higher order theory and not in second order arithmetics? In Kollenbach's higher order theory for reverse mathematics needed to prove A. That's a traditional RM question. The other, more untraditional, is given the construction in ordinary real analysis, what is the minimal set of non-computable tools we need to perform this construction? Well, for these questions to be precise, we need a basic theory for this first question, and we need a basic notion of computability. But I will deliberately be vague on this. Some natural candidates are the one introduced by Kleene in 59 or Gödel's T, but I will not be depending in my talk on either of them. Well, in his thesis, Platek proved the equivalence between Kleene's approach to higher order computability and an approach based on typed lambda calculus, or as he did, based on combinators. This partly inspired Scott to construct LCF, also known as PCF, as formulated by Plotkin. As a technical tool, Platek considered an intermediate type structure consisting of partial functionals only defined on hereditarily total arguments. It appears that he didn't consider this as important in itself. It was just in help in transforming the equivalence between various type structures. But this has turned out to be the most relevant type structure for studying some constructions in real analysis. So we come back to this. I will be interested in what mathematicians will consider as constructions. And this is not constructions in the sense of constructive analysis. It is simply what mathematicians think of constructions. And they may involve discontinuous objects. They may be discontinuous in themselves. So I include the first Cleanly quantify E2 as a basic non-computable tool. So everything I say will be relevant to E2 because the existence of E2 is equivalent to the existence of discontinuous functions. So if we want to treat mathematical analysis as mathematicians do, dealing with discontinuity phenomena, we naturally include E2 as a basic tool. Then I will vary on which other functionals we add, and indeed what model of computability we use, although I will not put too much emphasis on that in our analysis of the complexity of certain constructions. But I should say that positive statements, when I prove that something is computable in something else, I can normally do with a small fragment of Gödel's T. Recall that no deep computability theoretical argument that direction. While for the negative statements, I mostly prove them for modernized versions of the Kleene-Palatic calculus. So then, if you prove that something is not computable, it's not even computable in the cleanest sense. But it is computable, it's in a low fragment of Gödel's sense. Okay. Our concept of continuum is, as I see it, vague, as demonstrated by forcing. So I see it as a foundational interest to understand how much comprehension involving quantifiers over the continuum we need for various constructions in real analysis. And that is constructions involving third order parameters. As if you look at the mathematics from 1880 and up to 1920, there were a lot of those constructions, and they were not in as a part of second order arithmetic, but they were genuine third order mathematics, mostly. Well, objects as themselves will not be part of our model. Representations will, to some extent, always be needed. So the computability models we do consider will not accept that discontinuous functions phi from R to R directly as an input. It's not simply there, it has to be represented anyway. And what we do is gently to lift phi to a phi hat mapping bare space to bare space without adding any essential information. And that is quite important. That is in accordance with standard representations of the real numbers without adding any essential information. And I do not think of these as problematic representations. On the other hand, there are representations in computational analysis in the classical reverse mathematics. There are representations in the form of some function in bare space. This is the implicit information in the representation of this kind will often be richer than what is available from the object represented directly. That is, for instance, a modulus of continuity for a continuous function, or giving a G delta set. Well, you actually give the way the G delta set is described or defined. There is often an implicit theorem stating that a certain kind of object can be represented in a certain way. And part of our project is to analyze such theorems in the style of reverse mathematics and analyze the complexity of finding such representations in the tradition of higher order computability. So, more definitions. Let gamma be a class of countable. Let's take the example first. Let gamma be the class of countable subsets of R, including the finite ones. If X is in gamma, then the representation of X will naturally be an enumeration of X, or something close to that. And from a selection function from gamma, we can extract the well-known example of a set that's not Lebesgue measurable. Consequent, and from a representation, we can select the first element in that representation, for instance. So consequently, a map selecting one representation for each element in gamma will need a substantial use of AC. And that is a standard observation from the analysis of when you can have sections of equivalence relations over the Baire space or whatever, so there's nothing new in that. But we see that for certain representations, there will be impossible to find a representation just from the object represented, while for other objects, there will be this possibility. And that separates classes of functions or sets. What do I mean by objects of type of 0, 1, and 2? Well, the audience will recognize objects of type 0, 1 when seen. But objects of type 2 will essentially be subsets of the reals when I identify them with the characteristic functions, or they will be functions from the reals to the reals and similar objects. And I will only consider total objects of type 0, 1, or 2. On type 3, on the other hand, I will consider partial functions defined on total input. Let gamma be a class of subset X of R, identified with the characteristic functions. Omega gamma is then the partial functionals defined on gamma by omega gamma of X is 0 if X is empty and 1 if X is non-empty. So it's a partial subfunction of E3. And the selector for gamma is then in UT defined on gamma, such that it selects an element of every non-empty subset. But instead of normal quantifiers that's defined of every predicate of a certain set, we are only looking at predicates of a certain complexity over all of R, or if you prefer, continuum n to the n or Baire space. So this concept corresponds to a SCADA of search and selectors when gamma is the power set of some subset Y of 0, 1, which, yeah. So the cases studied so far are the set of finite sets, the set of sets with at most one element, the set of compact sets, the set of countable sets, F sigma G delta sets, the sets that are both F sigma G delta, and I may come back to that, there's a family of scattered set. So I write omega x and omega gamma x when x is one of these 8 cases. None of these are, by the way, computable in any functional type 2, so they're genuinely type 3 objects, and none are equivalent to a total functional in the sense of Kleene. So they are genuinely partial objects of type 3, and they are definitely of interest, all of them. So there's one particular known omega functional described in the literature. If gamma 1 is the set of class of singletons identified with characteristic functions, then omega gamma 1 is trivial because it will say yes, all singletons are non-empty sets. However, the one possible selector function is non-trivial. It turns implicit definitions into explicit ones. And this was originally called omega 1, and we stick to that name. And why is it of interest? Because this is a general oracle of type 3. You cannot, in any reasonable, computable way, find an element of a singleton, even if you know that the set is a singleton just from the set. You have to search over all of the continuum in order to be able to locate it. So we have proved that this functional is not computable in, for instance, infinite time Turing machines and other functionals or operations defined by transfinite recursion. Now we consider omega b and nu b. Let that be the associate selector. Modulo E2, we have that they are computably equivalent. And if you use the full power of Kleene computability, one can show that omega b can decide when a finite set is non-empty or not. But it is actually open if this is definable via a term in Gödel's T, and omega b is definitely strictly stronger than omega 1. indeed from omega b and a well-ordering of the continuum, you can compute E3. So it's pretty strong. Omega b was designed to compute the inverse of f from F and A, where A is a subset of R and F is the injective, and it's equivalent to that process of turning a function from a countable predicate, injective function from a countable predicate into an enumeration of that set. And the operator is equivalent to omega b. I think I skip a little bit. Functionals is extracted from constructions in ordinary real analysis will often be computable in omega b if they involve a step from an implicit definition of a finite set to an explicit description of one. And a key example is the Jordan decomposition theorem, where a key step in proving that or defining the Jordan decomposition in an effective way is to prove that a certain set that is finite because it contains no cluster points and turn that into an x1 to xn description. So when you prove that a set is finite, and then you say that let this set be x1 to xn, then you're indirectly using omega finite, and that is the complexity of that one. Okay, let's
Just
see.
so you know, there's about a minute left.
Mm.
We have about a minute more, a couple minutes, and then we need to wrap it up.
I didn't catch you. What?
You have 1 minute.
I have 1 minute only. Are you sure?
No, not me. Hey.
Okay. No.
Just a couple minutes to wrap. Yeah.
Okay. So these functionals are what we call lame. They cannot do not add any strength if you prefer only to compute relative to E2 and functions over bare space. So their strengths are genuinely shown on for type 3 object. So I think I can skip. So why are they of interest? They show that, for instance, the Jordan decomposition theorem, that is a construction, is a generally type 3 object. It cannot be carried out at relative only to type 2 functionals. And if you want to carry out that construction in the sense of second order arithmetic, you need a representation that is in itself of type 3. So, but I should say that omega b and the Jordan decomposition construction are computably equivalent. I skip what is of less interest, and I think I even skip omega c right now. It is just checking if a total closed set is not empty or not, and that is exactly computably equivalent to deciding the standard second order representation of closed and open sets. To find that from a closed or open set is equivalent to this functional omega c. We have a few other characteristics. So I want to move to some classical hierarchies. We are looking at the Borel hierarchy, and we are looking at the bare function hierarchy, which is based on pointwise limits of pointwise limits of functions, iterated starting with the continuous one. A natural question will then be when it is possible to select a way to generate an element in one of these classes. And for open and closed sets, omega c is doing exactly that job. We know by just saying that we can represent countable sets in those classes, that there's no way we can do that for F sigma G delta sets or for Bear2 functions. Topologists know how to use transfinite recursion to construct representation of Bear1 functions, and also for elements that are both sets that are both F sigma and G delta. And we have established that these constructions can be formalized as being computable in weak examples of omega function. And I have one example to look at it as scattered sets. I think I only have 5 minutes left now. Is that correct? 3 minutes.
Actually, a little bit over, so we'll probably need to wrap it up with this example. We're actually over time, so if you
I'm
could wrap.
over time?
Yeah.
Wasn't it 25 minutes now? Okay.
Oh, I think I know what happens is the schedule, he's not, you're supposed to have 5-minute
Yeah, we need
gaps.
a 5-minute between speakers, that's why, sorry.
That's not apparent from the schedule.
Sorry, that's our fault, yeah. Anyway, we can wrap it up with this example and then we'll change speakers, if that's okay.
So, okay. So then I think I should just close and go to the final fact, bearable functions. Yeah. Bearable functionals. If G is an arbitrary function of type 2, I say that G is bearable if G is a monotone and N is the only fixed point of G. Then I let less than or equal to G be the associate trivial ordering defined for bearable G. And I do have the following theorem. If G is bearable, then psi of G is computable in E to an omega 1, the one that just turned implicit definition into explicit uniformly in G. And psi is not computable in any functional H of type 2. And why am I interested in this? Because these functionals appear in all equivalences I have looked at between characterizations of Bear1 sets, of sets that are both G delta and F sigma, and so forth. If I look at Korotowski or other papers, they turn up that all the transfinite recursions they have can be represented as these bearable functions. So that's my final contribution. It's not a hard theorem. The proof of A is actually very easy, and the proof of B uses standard techniques from higher order computability. And then I think my time, according to my watch, is up. So I thank you again, Martin, and thank you all.
Thank you.